Okay, let's just jump right in. Welcome to this explainer where we are going to completely demystify the absolute powerhouse that is industrial instrumentation. Today, we're really focusing in on how industrial instrumentation systems work, how these massive, incredibly complex factories essentially run themselves. We'll be looking at the gold standard resources that actually teach this science to engineers all over the world. So, if you've ever found yourself wondering how a fully automated modern system does its thing day in and day out, you are absolutely in the right place.
To control a process, you must first be able to measure it accurately. That idea right there, which is inspired by foundational engineering text from Doebelin and Liptak, is the non-negotiable reality of basically any industrial system. Before we can get robots to assemble cars or get a refinery to process oil, we have to gather precise, real-world physical data. It's simple, really. You just cannot control what you cannot measure.
So, here is our roadmap for the explainer today. We're going to cover 1. The blueprints of instrumentation. 2. Fundamentals of measurement systems. 3. Mastering process control. 4. Simulating the systems. And finally, 5. Global standards and calibration. All right, let's kick things off with Section 1, the blueprints of instrumentation. These are the foundational texts that really define the entire industry.
Taking a cue from how Khan Academy breaks down complex topics, I want you to think of industrial instrumentation like the anatomy of a living, breathing factory. The sensors out there on the factory floor, those are the senses. They are constantly seeing, feeling, and hearing the physical environment. Imagine for a second a massive, superheated steam pipe. A temperature sensor attached to that pipe is literally feeling the heat 24/7. If there's a sudden, dangerous spike, it detects it instantly. But, a sense is completely useless without a brain, right? Well, the controllers act as that brain. They take in all that raw sensory input in real time, process it in the blink of an eye, and make really critical decisions, like sending a lightning-fast command to throttle a cooling valve before that pipe bursts. It's this continuous, invisible nervous system keeping the whole shebang running safely.
And mastering this factory anatomy doesn't happen overnight. It happens in very specific stages. An engineering student usually starts with Patranabis's core principles, just getting a grip on the basic physics. Then they dive into how to actually capture that physical data, using analysis textbooks by Sawhney and Doebelin. Once you figure out how to measure, you have to learn how to control the process, and that is where Johnson's work comes in. Finally, engineers graduate to the advanced, real-world applications found in Liptak's massive, comprehensive handbook. It is a complete journey, straight from theoretical physics all the way to running a fully automated assembly line. Moving right along to Section 2, Fundamentals of Measurement Systems. This is all about gathering the data.
Like we said, before the brain of our factory can do any thinking, the senses absolutely have to gather the data. And authorities like Sawhney, Nakra, and Doebelin, they provide the definitive guidebooks on exactly how to do this. They teach engineers the incredibly cool mechanics of translating physical reality into a language that computers can actually understand. I mean, think about the intense pressure inside a chemical reactor. You can't exactly just plug your laptop into a vat of boiling chemicals. You need a transducer. These books teach us how to design devices that physically flex under extreme pressure, and then how to convert that tiny microscopic flex into a measurable electrical voltage. That voltage is your data. These aren't just dry textbooks, they're the literal instruction manuals for designing the eyes and ears of automated industries.
Which perfectly tees up Section 3, Mastering Process Control, Acting on the Data. Getting your head around the transition between gathering the data and acting on it is the absolute secret sauce to all modern automation. We call this the feedback loop. First, your measurement systems gather super precise data from the physical world, like, say, tracking a sudden drop in fluid flow inside a critical pipeline. But again, raw data just sitting there doesn't solve anything. That is exactly where process control, championed by experts like Curtis D. Johnson, steps in. This is the mechanism that receives the data, compares it against whatever your desired target is, and instantly makes a corrective decision. So if the flow rate is too low, the process controller automatically opens a motorized valve just a tiny bit wider to compensate. Or if a chemical reaction starts running way too hot, it immediately triggers the cooling system. And it's doing this thousands of times a second, tweaking heaters, valves, and belts without a single human ever having to step in.
Now, actually integrating these two phases, the measurement and the control, is mind-bogglingly complex. Just picture a massive oil refinery. You aren't just looking at one single temperature sensor, you are dealing with tens of thousands of raw, noisy electrical signals from pressure transmitters, flow meters, and level sensors all firing off at the exact same time. And they all need to be instantly interpreted by a central brain without any interference. Because this is such a massive engineering hurdle, elite institutions like MIT actually offer free OpenCourseWare to tackle it. These resources give you the rigorous mathematical and architectural background you need to understand how thousands of crazy, diverse data points can integrate seamlessly into one perfectly choreographed system.
All right, let's jump to Section 4, Simulating the Systems. Here we'll look at interactive application in the curriculum.
Look, you can't just read a book, ace a test, and suddenly know how to run a multi-billion-dollar oil refinery. The margin for error out there is literally zero. One bad calculation in a control loop could ruin entire product batches, or, even worse, cause a catastrophic explosion. To solve this super high-stakes problem, the Indian engineering curriculum is doing something really brilliant. They leverage a vast, incredible ecosystem of free digital resources to bridge that huge gap between textbook theory and actual factory floor practice. They use interactive digital simulations so engineers can test systems, make all their mistakes, and learn the ropes before they ever touch real, dangerous hardware. Through platforms like NPTEL, students are getting deep-dive video lectures straight from esteemed IIT faculty. But for me, the real game changer is the Virtual Labs project from institutions like IIT Delhi and IIT Kharagpur. These digital labs let beginners safely interact with and run experiments on virtual sensors and controllers that mimic real-world physics flawlessly. A student can literally push a simulated industrial boiler way past its critical pressure limit just to see exactly how the automated safety systems react. You get to tune complex control loops and watch the system respond in real time, and it's entirely risk-free. It's such an engaging, absolutely crucial step for getting a deep feel for these mechanics before stepping into a live environment. And finally, we arrive at Section 5, Global Standards and Calibration, the global rulebook.
This is basically the glue that holds the entire global industry together. Think about our modern supply chain for a second. A highly specialized pressure sensor built in Germany might end up installed in a chemical plant down in Brazil, which is operated by a control system that was programmed in Japan. For all of those different parts to talk to each other perfectly, the ISA, the International Society of Automation, sets the global standards for instrumentation symbols and process control. They ensure everybody on Earth is speaking the exact same engineering language. Meanwhile, you have the ISO dictating the strict rules for measurement and calibration, guaranteeing that 1 kilogram of pressure reads exactly the same everywhere on the planet, down to the microscopic level. Without this incredible level of global coordination, integrating these systems would be literally impossible.
So, as we wrap up this explainer, I want to leave you with a question to chew on. When you consider everything we've just covered, from the foundational physics of a single sensor all the way up to massive digital simulations, how does standardizing symbols and calibration across millions of automated factories ultimately impact the speed and the efficiency of our entire global supply chain? Because honestly, without these rigorous global standards, our modern automated world would probably collapse into total chaos overnight. It is a wildly fascinating ecosystem, and I highly encourage you to check out some of those resources like MIT OpenCourseWare or Virtual Labs to dive even deeper into the invisible systems that run our world. Thanks for tuning in.